So this is the Daily Workout Book 1, and although there are answers towards the rear of the book, I also have these on the website that you can download. And in this video, I'm just going to be going through all of my answers that I wrote in here. So some of them straightforward. We're going to just look at the area of a circle. This comes up all the time in A-level physics, often to do with things like the diameter of a wire. So the area is just pi r squared. And what's important to do is make sure that you convert from centimetres or millimetres into SI units, and these are the answers I got. The next one, this is just a tip-to-tail vector diagram working out the magnitude and measuring the angle from the vertical. So this one, it's worth making sure that you spend a bit of time using your ruler, using your pencil, and again just using your protractor to measure the angle. If you know the length of this line here, in this case that's in kilonewtons, you can work out the scale, and then if you measure the length of this in millimetres, you can then convert that to the appropriate number. And we're looking for a number of about 8.9 and about 80 degrees. Obviously, when you're doing scale drawing, the numbers aren't always going to be the same all the time. The next one, we've got the 7 base units, so all other derived units. So a derived unit could be something like the Newton, but we can also express the newtons in one of these 7 base units. So we've got mass, length, time, current, temperature, the amount of substance, and luminous intensity. The candela, this is something you won't have covered at GCSE, and to be honest, we don't really actually ever use it at A-level, but it's just one of the 7 base units. Okay, going on to the second. Again, we've now got the same equation that the area is pi r squared. You can work it out, and you'll notice that when you've got quite a small radius, the area is actually a really, really small number. A and C, they both have the same data. So we've got the radius of 5 millimetres or the diameter of 10 millimetres. That's basically the same question. And for this one over here, for B and C, we could use the equation that the area is equal to pi d squared over 4. And that's, again, something which is an equation that I think is really useful in A-level physics, because you're often given the diameter of something rather than the radius. And to work out if you know the circumference, well, we know the circumference is 2 pi d. We can use this to work out the diameter. We could use it in that equation, or we could just substitute this into that equation and find that the area is equal to c squared over 4 pi, which is 8 times 10 to the minus 6 square metres. Now, A-level, there's going to be a lot more symbols that you use, and a lot of these you can find in your data sheet. Big G stands for the gravitational constant. This symbol here is a Greek letter epsilon, and epsilon naught is what we call a permittivity of free space. It's basically how well an electric field can be transferred, and this comes up all the time in year 13 when you're looking at electric fields. PC is the parsec, which is another unit for measuring astronomical distances. You might be familiar with a light year. A parsec is another measurement for these big distances in space. Little h is Planck's constant. This comes up a lot at the end of year 12 when you're maybe looking at quantum physics. EV stands for electron volt, and that's another way that we can use to measure energy. So if you've got very small energies, sometimes a joule isn't the most appropriate unit, and therefore an electron volt is more useful. And ME, just the mass of an electron, that's going to come up all the time, 9.11 times 10 to the minus 31. Now for this, show that the base units for joules are kilograms meters squared seconds to the minus 2. So what we have here are our base units, and we saw those on the previous page, kilograms, meters, seconds, and so on. And I just used this equation here that said kinetic energy is a half mv squared. You know that equation. Now kinetic energy is measured in joules, and if we look at what that is in these base units, a half is unitless, that's just a number. We measure mass in kilograms, and we measure velocity in meters per second. Because we've got meters per second squared, effectively I'm going to multiply meters by 2 to become meters squared, and seconds to the minus 1 is multiplied by 2 to become seconds to the minus 2. And if we multiply these together, we can also say that a joule, or 1 joule, is 1 kilogram times 1 meter squared times 1 second to the minus 2. Now, that's something you won't have done at GCSE, but it's something that you will be familiar with, often covered at the start of the A-level course. So that one over there is how we can show the base units for joules are kilogram metre squared seconds to the -2. 3rd of August, calculate the area in metres squared of a triangle. So a triangle is just a half times the base times the height. I put the numbers in here. I gave this last one to 3 significant figures because it's to 3 significant figures in the question, and I converted that into metres to make sure that we had our areas in square metres. This one over here, like the previous page, we start here. Although we go around this way, we end up over here. And again, just using the ruler and the protractor, I got a value of about 6 kilonewtons and about 53 degrees. In this case, going, I suppose, anti-clockwise. So going this way rather than going that way. Okay. Calculate the horizontal and vertical components of a 10 Newton force acting at 17 degrees above the horizontal. So for this, we've got basically the horizontal component, which I've called FH. The vertical component is FV, and that length there is going to be the same length as this side. So we've got a right-angled triangle, which means we can use a bit of SOHCAHTOA. Now, if you're not sure, you can still write it out. And that means you make sure that you're using either sine or cos. Now, another way to remember it is this angle here is the closed angle, okay? And therefore the closed angle is cos. And that's maybe, again, a shorthand way of remembering it. So I just used the resultant force times either sine or cos of the angle to get these values here. The 4th of August, and we started looking at the surface area of a sphere. And we had these values which got smaller by a factor of 2 each time. So we halved it, and we halved it. When we look at the surface area, what we notice is that the surface area goes down by a factor of 4. So here we're dividing by 2, here we're dividing by 4. Okay, and you divide that by 4 again, divide it by 4 again, and that's the pattern that we see with the relationship between the area, which is metres squared, and the distance, which is metres. Now the next one, again, this is something that you never have to remember all of these off by heart, but you will be using these again and again and again, and you'll be very familiar with these relatively quickly when you're learning this new content at A-level. So we've got the mass of an electron, Planck's constant, 6.63 times 10 to the minus 34 joule seconds. The speed of light, you probably remember that already. And then the elementary charge, the smallest charge that these particles have, is 1.6 times 10 to the minus 19 coulombs. The gravitational field strength on the Earth's surface, we often use the value of 9.81 newtons per kilogram. And that means that the acceleration on Earth's surface is also 9.81 meters per second squared. Really, gravitational field strength should be measured in newtons per kilogram. Okay, and although this does vary in places around the Earth, this is the value that we use for A-level, not 9.8, not 10. Now for this one, calculate the direction of the resultant force. It's so important to draw a diagram. It doesn't have to be super neat, but we can see here we've got 9.81 to the right, 3.24 down, they're acting at right angles, and therefore to find the direction, we just used tan to the minus 1 of opposite over the adjacent. This gives a value of 18.3 degrees to 3 significant figures, and that's below the horizontal. So this one here, we didn't need to work out the magnitude, we didn't need to use Pythagoras, we just needed to work out the direction. On to the 5th of August. We're now going to use the equation that says the volume is equal to 4/3 pi r cubed. Okay, we've got an r cubed because we're looking at a length times a width times a height effectively, and that's why we've got this r cubed here. Again, what we're doing here is we're going down by a factor of 2 each time, 0.8, 0.4, 0.2, 0.1. And if you notice the pattern here, what's happening is that we're going down by 8 every time, because that's the same as 2 cubed. And therefore we've got 2.1, and really you only have to do this equation once, and you could divide by 8, divide by 8, and divide by 8. Again, keeping all our answers to 2 significant figures. What's the relationship between gravitational potential energy and the mass? Well, EP equals mgh, and this is for something where we have a uniform field. Okay, so that's what we approximate this gravitational field to be on the Earth's surface. It's only really where you go a long way away from that object that we maybe think about the radial field, and there the value of g doesn't stay constant. But let's not worry too much about that at the moment. That's something coming up in a couple of years' time. And again, for potential energy, we can use EP or PE. Anybody looking at your work will understand what you mean by that. Now, this one, calculate the combined resistance of a 30 and 50 ohm resistor connected in parallel. So some of you might have seen this at GCSE, but a lot of people won't. Now, this is the equation we're going to use, and this was given to you at the front of the book. What I have in the first couple of pages is somewhere for you to add any data and formula that you might find useful. Now, you don't have to fill the whole thing up. I mean, you could easily fill it up, but this is things that maybe you're not familiar with. And I've got here resistors in parallel. So here, 1 over the total resistance is equal to 1 over this resistor plus 1 over this resistor. Now, what a lot of people do, and I've done this myself so many times, is you say 1 over RT is this plus this, which is 0.05333. But you've got to take the reciprocal. You've got to do 1 divided by this number to get the final resistance, 18.75, which is about 19 ohms. And you'll notice that if we've got a 30 ohm resistor and a 50 ohm resistor, their total resistance is less than either of these values. Okay, some of you might have seen this at GCSE, but this is just introducing that next little bit of A-level. More resistors in parallel decrease the overall resistance. Okay, 6th of August. We've got a very, very long cylinder. Okay, basically it's a piece of wire or something like that, or like a very thick cable. So we've got the radius, we've got the length. The volume is going to be equal to pi r squared L. That's just the volume of a cylinder, which is 0.072. Now, to work out the surface area, what we've got to do is we've got to think about the surface area of each end. Okay, that's just the area of a circle, pi r squared, and we've multiplied that by 2. So that's the area at each end. Now, in terms of the surface area of this long bit of the cylinder, that's going to be equal to the circumference, which is 2 pi r, multiplied by the length, because it's basically unwrapping it into like this big rectangle. And that's a surface area of 1.6 meters squared. Now, trace the following curves. Use a pencil in case you make a mistake. Now, what I haven't done on my answers is do this. When I wrote these answers in, I actually used an iPad, which is actually quite difficult to draw these curves in. Now, my approach for things like this is to move the piece of paper around, okay? So keep your hand on the inside of the curve. If it's not perfect, it doesn't matter. What I'm trying to get you to do is think about, in the future, if you've got some data with a curved line of best fit, you can put an appropriate line through. Now I'm just going to do one motion. That's pretty good for my first attempt. Okay, now the second attempt is going to be difficult because it's a tighter curve up here. Okay, I've stopped the line. That's not what you want to do sometimes. You want to just keep it going. Okay, so that's okay. Maybe this bit here is a little bit wiggly. It's not perfect, but I think it shows the trend in that data. Now, if you make a mistake, not a big problem. You don't have to tell anybody about it. And if you're using a pencil, you can just rub it out and put something in better. What you don't want to be doing is if you move too slowly, you get a line that ends up a bit like jaggedy like that. You definitely don't want to be sort of doing something like this. Yeah, so, you know, stuff like this, it's just not good enough. One smooth line is better than that, but that will come with practice and you'll have many more attempts in the book. The next one, we've got a stone launched vertically upwards, but we don't know how heavy that stone is. But what we're going to do is equate the kinetic energy, EK, and the potential energy. So we can say that half mv squared equals mg delta h, and here the m's cancel. It could be 2 kilograms, it could be 20 grams, it doesn't matter. The mass cancels, and therefore the change in height is equal to v squared over 2g, which is equal to 32 meters. And here we were looking at the conservation of energy to solve this problem. Another approach could be to use a Suvat equation, where s is our change in height, v is our final velocity, and at is going to be where A is equal to that gravitational field strength. And also, if you use this Suvat equation, you'll get something looking very similar, which gives you the same answer. Okay, 7th of August, calculate the volume and surface area of these spheres. with this radius. Again, you're going to use v is equal to 4/3 pi r cubed, or a equals 4 pi r squared. You'll be given this in your data book, but if you're doing A-level maths, if you've done GCSE maths, you know this stuff. So you do the calculations, and these are the numbers we get. We arranged to make t the subject. So here, t, frequency is 1 over time period, t is just 1 over f. You'll be familiar with that from GCSE. This equation is actually not always used by everybody doing A-level physics, and this is to do with the torque experienced by an object. So here T is torque, and here T is standing for the absolute temperature on the Kelvin thermodynamic scale. And finally, for this one over here, T is also the temperature, but now we've got T raised to the power 4, and that's often to do with the temperature and the power, or the energy emitted per second, by something like a star. Now for this, we've got two equations, v equals f lambda, f equals 1 over t, and you could work out the frequency and then substitute it in, but what I did was I combined these two equations together to say that v is equal to lambda over capital T, and again, capital T is the time for one wave cycle, and here that just gives a value equal to 10 meters per second. So there we go, that's the first week in August complete. So starting on the 8th of August, we're going to use the equation that says the area equals pi d squared over 4. I think you should just get used to using this quite a lot. I do find it incredibly useful. I've rearranged it to make d the subject, and therefore these are the answers. Now it might be worth pointing out that for C, if you're converting from millimetres to into metres, you've got 10 to the minus 3. But we've got millimetres squared, we've got 10 to the minus 3 times 10 to the minus 3, which is 10 to the minus 6 square metres. Okay, the next one, we've got omega, which is a Greek letter. Now, omega can be used for things like angular frequency or angular velocity. Now, you've probably never seen anything like this beforehand, and some of you might never will, depending on which modules you might be doing later into year 13. Some exam boards like AQA have an optional topic where you can look at rotational motion in a bit more detail. So these ones over here, power, torque, and omega is equal to P over T. Omega is equal to V max, the maximum velocity divided by the acceleration, F over mr, or 2ek over I. Again, it doesn't really matter what the symbols are. I'm just wanting you to practice rearranging equations, an essential skill. The next one could be a GCSE question. You've got something with an initial activity. So A, the initial activity is 2000 becquerels, the unit that we measure. And after 4 half-lives, what I've done is said, well, okay, after 0 half-lives, there's an activity of 2000. After 1 half-life, it's going to drop to half its original value. After 2 half-lives, it's going to half again, and half again to 125. So that's a very simple way of doing it. We've got the volume of a cylinder. So again, we can either use pi r squared h. This one over here, because we've got the diameter, we've got pi d squared over 4 times the length, or pi r squared L. Okay, and it will give you these values. Now we're going to make V the subject. This one you're familiar with about density is mass over volume. So we've got the volume represented by here. Here, V is representing the potential difference. So V equals IR. You'll know that equation from GCSE. We've now got the ideal gas equation where we've got the volume, or here, P equals V squared over R. Again, V is standing for the potential difference. So context is important. But again, hopefully you'll start to recognise some more of these symbols. Now at GCSE, a lot of you will have said that PV is equal to a constant when we have this ideal gas. If you multiply the pressure by the volume, you'll get a constant value. And that means the pressure times the volume before is going to be equal to the pressure times the volume afterwards. So this question is based on your current GCSE knowledge. I've said that P1V1 equals P2V2, and I've rearranged this to make P2 the subject. And then it's often actually useful to maybe write by the side of over here, maybe what's P1 and what's V1 and so on. So this is our initial volume, V1, at this initial pressure, P1, and the volume is decreased, so that's now V2, and we want to know P2. Now for this, as long as the units are the same on both sides, it doesn't matter because the units cancel. So that's our ratio of V1 to V2. And the pressure is 220 kilopascals. And that would then give a final pressure of 1100 kilopascals. Or you could have said 1.1 times 10 to the 6 pascals. Okay, I just kept it in the same units as the initial thing that we had over here. Okay, so that, although you might be doing more stuff like this in year 13, this is based on what you should know, a lot of you, if you've done triple science or separate physics from GCSE. 10th of August, we've just worked out the gradient, which is just equal to 1, and then y minus y1 equals mx minus x1. We've just rearranged some more equations. Most of these are fairly straightforward. Here we've got v standing for the velocity, and actually all of them. So there's this link between power and the force. There's this equation, which I think is super important. It's called the Lorentz equation, and this is often to do, or the Lorentz force, and this is to do with the force experienced by a charged particle moving in a magnetic field. That's going to come up a lot in year 13. We've got this equation looking at the centripetal force on an object, and this one some of you might see, and this is to do with the redshift, or the change in frequency of a wave emitted by an object travelling at a certain speed. Okay, number 3, a two-part question. I've just drawn a quick diagram. This is my motorbike. We've got the forces acting on it, and therefore we can work out the resultant force as 1400 newtons. We know that the mass is going to be related to the weight by g, and therefore we can work out the mass. And if we put these two numbers in, we get an acceleration of 4.91 meters per second squared. On the 11th of August, again like we did yesterday, we've just worked out the gradient. Here we've got a negative number over another negative number, so that gives a gradient of 3, giving y equals 3x minus 13. We're now going to make r the subject, so r is the radius here. This is to do with torque. This one over here, we've actually got the force on a falling object through liquid. Again, some of you will never need to use this at A level, but that doesn't matter. This is just practice at rearranging these equations. We've got F equals m omega squared r for the centripetal force yet again. And again, r is just equal to v squared over a. So hopefully you're getting more used to this by now. In this question here, we've got a mountain biker accelerating. I like riding mountain bikes, that's why there's this question here. You also might hear some drilling in the background. I don't know if that's being picked up by the speaker, but yeah, the office just down the corridor from mine, they're just doing some work. So hopefully I can hear it. I don't know if you're picking it up, but hopefully that won't interrupt you too much. Okay, I've just written down SUVAT. It's a motion question. I've filled in what I know. We don't need to know the acceleration, and we haven't been given it, so I've just crossed it through. And what we're trying to find out is the final velocity, okay? Because we're going to use that later to work out their change in kinetic energy. So I use the SUVAT equation to find that their final velocity is 8.5 meters per second. And that meant when we put this into the original equation, this gives a value which to two significant figures is 4,000 joules. 12th of August, yet again, we're going to work out, because we've been given now the gradient, which we put over here, we find that the line of y equals mx plus c is equal to minus 2x plus 21. Now, I haven't included many practical equations or practical questions yet, and I'm going to add more of those in future books. But in a practical investigation, the independent variable is what you decide to change, and then you measure the dependent variable. And what you do with the control variables is you keep these the same to ensure a fair test. It's pretty much as simple as that. And you're going to be doing many practicals and see many practicals as you go through the course. And here, we want to find the range of frequencies. Now, all of these are going to be travelling at the same speed. We've got the wavelength, which I've converted into meters, so it's 700 nanometers, so 700 times 10 to the minus 9. And that means visible light going from red, 4.3, to violet at 7.5 times 10 to the 14 hertz. So that's the range of frequencies of visible light. And on the 13th, we're going to be, again, finding the area in meters squared of a circle with a diameter. You'll have done this beforehand. Just make sure you convert to standard SI units. And what we have over here is centimetres, millimetres and micrometers, or micrometers. Okay, we've now got a couple of curves, and again you can trace the line. Again, I said about before, if you get your pencil and and you keep your hand on the lower side of the curve, what you can then do is keep turning that paper around. Okay, this is not my best sine curve, and if yours isn't perfect, it's nothing to worry about. You have plenty more chances to practice them. So what we have here is a shape which is y equals sine x. Okay, so it starts at 0, goes up, goes down, and goes up again. This one over here, it goes down before going back up. And again, what I can do is maybe just have a go at doing a better curve for this one. Again, just turning the paper to hopefully get an appropriate shape, which is approximating a sine curve. Okay, so you can see now it starts at 0 and goes down, and therefore y is equal to minus sine x. This one over here, quite a lot of work to do, but the best thing to do is just start by drawing in your diagram. So we've got two resistors in series, a 6-volt battery, current of 3 amps. So I've just labelled it, and I've used different colours. You don't have to do that, but for this to help my explanation, I used red for the current, green for the potential difference. If you're colourblind, that's green and that's red. And then I used blue for this colour over here. I just kind of basically went through my simple equations from GCSE and applying them at the right time. So the total resistance is equal to the potential difference divided by the current, which is 20 ohms. And that means if you know the total resistance is 20 and that's 12, that must be 8. And then we can look at the potential difference across these two things. So that's 12 and that's 8. And what we then found was that the bigger resistor had a bigger potential difference across it of 3.6. The smaller resistor had a smaller potential difference across it. So the resistance is proportional to the PD across it in this series circuit. And the 14th of August, again, what you can see here is you're just having a go at sketching these curves. It's maybe quite faint, but all you need to do is just practice doing it again and again and again. This time you've got the line to kind of follow. Now what we're going to do is we're going to sketch it with the same amplitude and twice the frequency. Now my approach for this, it would be using a ruler. I'm just going to draw maybe a line along the top, and this means when it comes to constructing your graph, you have the same maximum and minimum values. But now what I'm going to do is put a line here and here. So what I've done, I've split that in two. I'm going to split it in two again, like so. Now that's one normal wave cycle. If it's got twice the frequency, the time period will decrease. So basically this is going to be the end of my first wave cycle, and that means rather than this being the peak, that's going to be the middle, and here we're going to have a peak, and here we're going to have a trough. Now this is just my rough kind of sketch. We can then put in our wave that goes up, and again moving the paper away from you like this, like that, and so on. So what you can see here is I've done something with the same amplitude, twice the frequency, so half the time period. And you should do that for the rest of this wave. It's going to be time consuming, but it will pay off. When you get questions like this in the future, they're going to be easy to do. Okay, number 3, we've got the half-life of a sample, and we've got the number of nuclei, which is n. Okay, the number of original nuclei left after 1 day. Well, 1 day is 8 half-lives, and each, because you've got 24 hours divided by 3 hours to give 8 half-lives, the total amount left is going to be 1 over 2 to the 8, which is 256th of the original amount. So if you've got the original number, times it by 1 over 256, that will give you 2.5 times 10 to the nuclei left. Okay, so something there with a relatively short half-life. So now you know how to do this one here. Again, I'd use your ruler and a pencil to draw in the lines to help guide you. So we want to have half the amplitude, so it's going to be lower down. 4 times the frequency means it's going to have a really, really short time period. We've got some values here. Again, you can find these in data sheets. You can just Google them. Avogadro's constant and the molar gas constant, although you might have seen these and you will be using them if you're doing A-level chemistry. These also come up when we look at ideal gases. We've got big G, the gravitational constant, and the elementary charge once again. For this one, again, I'm going to use the equation that says P1V1 equals P2V2, and that's because for an ideal gas, the pressure times the volume is always going to be a constant value at a constant temperature, and that's why the pressure is gradually increased. So here, I use this to find V2 as 16.3 centimetres cubed. Now, a centimetre is equal to 0.01 of a metre, so you've got 1 times 10 to the minus 2 times 10 to the minus 2 times 10 to the minus 2, which is 10 to the minus 6. So that's the answer for that final volume. Right, the 16th of August. Yeah, these numbers, basically, we don't really tend to use these much in A-level, but it does say in the specification. So 10 is bigger than 9, 100 is much bigger than 9, 3.7 is smaller than 4.1, and this one over here, we've got these two numbers. So I'd suggest writing this number in normal standard form. Often when we're looking at the wavelength of light, we're given something in nanometers. That's why I've got 660 times 10 to the minus 9, but that's just 6.6 times 10 to the minus 7, which is only a little bit bigger than this number over here. We've now got different values of omega. We've got omega 1 and omega 2. Actually, these are equations that only some of you might see if you're doing an engineering physics option at the end of year 13, if you're doing AQA. But what we have is some equations which are a bit like the Suvat equations of motion, but Suvat are equations of motion in the linear direction. These are the equivalent Suvat equations, but for rotational motion, where things speed up or slow down. So we've got these things over here. These are a little bit difficult to write in the answers, so hopefully that makes it a little bit clearer. Now, force is equal to the spring constant times the extension, and also which we've got over here. Now the area under that graph is going to be equal to a half the base times the height, so a half times F times E. And we're going to substitute this in to say that the energy stored is equal to a half KEE, which is a half KE squared. Okay, I should have probably put an E on that as well. Okay, 17th of August. We've got some numbers here. They all have a meaning. There is like a method in my approach to these questions. So we've got the mass of the Earth and the mass of Venus. We can see that the Earth is a bit bigger than the mass of Venus. But when we compare the mass of the Earth to the mass of the Sun, it's about 1,000,000 times smaller, so a lot less massive. This one over here, it's a big number, but I put it into standard form. That is 6.00 times 10 to the 30, which is a lot bigger than this, so that's a lot smaller than that. And finally, the mass of an electron, 9.11 times 10 to the minus 31. Well, that's just very slightly smaller than 1 times 10 to the minus 31. Now, although that's the minus 31 and that's the minus 30, that's because we could also say that's a bit like 10 times 10 to the minus 31, which is 1 times 10 to the minus 30. So we can see that this number is almost this number, so it's only a little bit smaller. Now we're going to make lambda the subject. Lambda is often used as the wavelength of a wave. So we've just rearranged it here. This equation is to do with diffraction of light and a diffraction grating. This one is to do with a double slit, and this one is to do with some astronomy and looking at, I can't remember actually. I think this one here is used when we look at a resolution of a telescope. I can't remember exactly, but again, I've got a video about it, and this is often covered at the end of year 13 for some students. For this one, what I did was I resolved this force into its horizontal component, so it's 350 cos 30, took away this to find out the resultant force. In this case is going to be in that direction is 133, and we divided that by the acceleration to get the mass as 130 kilograms. On the 18th, we're doubling the frequency, twice the amplitude. Again, use your pencil when it comes to working this out and spend the time doing it. I know it takes a while to do, but if you put in your kind of construction lines at the start, it's going to make everything so much easier. Now we're going to make R the subject. Again, we've got some equations that you don't need to know about, but here we've got KQ over V is R. Now we've got something, maybe not with the potential, but with the electric field strength, and we've got an R squared. We've also got the force. This equation is, well, these ones here are to do with electric fields, and this one is to do with a gravitational field. to say that the size of that radius is equal to gmm over the size of the force square rooted. Sometimes you might notice that this equation has a negative symbol, and that just means that we have an attractive force. Here we've got something moving up. We've equated these two things and we've rearranged. I could have worked this out and put the numbers in, but I just rearranged into one massive equation of ke squared over 2g delta h. I put the numbers in one go to find that the mass was equal to 2.84 kilograms. So the word sinusoidal just means cos or sine, and you can see I've already started it here for you to kind of follow. So I would maybe look at the distance for one wave cycle. You want to keep that fairly consistent. You can obviously measure it out and also use your ruler to kind of get the same height each time. So these construction lines can really help you. Now this seems super simple. We're basically looking at angles, but that's going to be so important. With a z angle here, so a equals b, we know that these angles add up to 180 degrees, and this one, which is opposite this one with these two lines, b is again equal to a. Now, data, identify the anomaly. It's the one that doesn't fit the pattern, so here it's 1.2. And to calculate the average force, and in physics A level, when we talk about the average, most of the time, like 99.9%, we talk about the mean. And here, I've discarded the anomalous data. So this one here doesn't count, and that's why I've just added up these 4 bits of data to work out the value as 2.2. Okay, on the 20th. So you don't even need to actually get the definite values, but the Earth is a lot smaller than the Sun. Now this thing you might need to Google actually. Now a lot of the time we give the mass on of a proton and a neutron, especially at GCSE, as 1 unit. But actually the proton is very, very slightly lighter than the mass of a neutron, but the mass of a proton is much bigger than the mass of an electron. Now this one over here, a black hole, generally what's left behind after a star's supernovaed, that mass is going to be incredibly big and it's going to be greater than the mass of the Sun. However, like everything in physics, when you delve a little deeper, sometimes black holes have stellar masses, so the actual core that's left behind has the same mass as the Sun, but it's just super compacted, and that's why it can make a black hole. So a lot of the star has been ejected in the supernova, that's been kind of shot off into space as the core collapses and the outer layers bounce off what's left behind. And it might mean that the black hole might have a mass similar to the mass of our Sun, but because it's so concentrated, the gravitational force is so much that our normal Newtonian physics stops working. Okay, a bit more angle stuff here. You should be okay with most of this. And then using a wavefront diagram. So the wavefronts, that's effectively the point where you have all the parts of the wave which are in phase. Often we draw rays to show the direction of light, but we can also draw a wave with a wavefront. And the reason that refraction occurs is because the wave crosses a boundary and part of the wavefront slows down before the rest of it. In actual fact, I filmed this with a drone and my car. So you'll see here now that as the car approaches a different medium, one of the tyres hits before the other tyre. It changes direction, goes at the same speed through it, and then as it comes out the other side, it then speeds up and changes direction. Right, on the 21st, you need to draw a sinusoidal curve. So again, just practicing this. So have a go at doing this lovely sine or cos curve. A and B is 180, and C and D, you can use this equation that basically this and this must equal 180 to find that that's equal to 133. Straightforward, easy stuff. Gets a bit more complicated now because we've got a netball, and we're going to assume the bottom of the netball is 1.45 meters above the ground. So this distance S is equal to 1.45 meters. I've written down SUVAT. I've identified what we do and don't know. Now to work out the final velocity, I've used v squared equals u squared plus 2as. U squared is just 0, and that gives my final velocity, which I've then used to all its significant figures in this equation here to work out the time of flight, which in this case is equal to 0.544 seconds. Okay, good bit of SUVAT there. On the 22nd, this is a challenge, okay? If you spent a lot of time yesterday getting in a beautiful curve here, which is perfect, I want you to try and do better today. Angles, straightforward. Here we've got the general formula for alpha decay, and alpha decay is when 2 protons and 2 neutrons are ejected from the nucleus. So we can use an alpha symbol, the Greek letter alpha and 2, 4, or sometimes we use a He symbol because it's the same as a helium nucleus. And whatever element X starts as, this number goes down by 2, that goes down by 4, and we change the type of elements. Conservation momentum. This applies to a closed system. So the momentum before is equal to the momentum afterwards for a closed system, provided there's no external force being applied. Reflection, well, basically it's when a ray of light bounces off a surface, or a wave bounces off a surface, and you've got specular reflection, where everything that comes out goes off in the same direction, like you'd get maybe with a mirror. You also have diffuse reflection, where because of that rough surface, all the rays of light or the wave moves out into different directions afterwards. Now we're going to use the equation. Again, you'll have seen this at GCSE about the change in pressure with depth. We've rearranged this to work out the depths underneath, and the atmospheric pressure is 101 kilopascals. So that's 101 times 10 to the 3 pascals. So you'd have to dive down 10.3 meters to effectively double the pressure on your body. What is the amplitude of a wave? Well, it's basically the maximum displacement from its equilibrium position. And the amplitude is always given a positive value, but the displacement could be positive or negative. So that's what we mean by the amplitude. And the difference between a DC and how the electrons actually move is in a DC direct current. We say that conventional current goes from positive to negative, but in an electric current, the actual electrons are moving away from the negative and towards the positive part of that cell or battery. Again, this is based on your GCSE knowledge. We know that force equals mass times acceleration, and therefore, because acceleration is v minus u over t, we can say that force is equal to mv minus mu over t, which is our change in momentum over time. So, for the same change in momentum, the force is proportional to 1 over t, because this delta p would be the same value, and that means they are inversely proportional to one another. If you increase the collision time, we decrease the force experienced. Now, you will be doing a lot more work on waves, but at GCSE we might have looked at longitudinal transverse, often shown with a slinky. So I just did a diagram of a slinky. If you wave it from side to side, the energy is still being transferred this way, but the vibrations or oscillations are at 90 degrees. And that's what we have when you have a transverse wave. With a longitudinal wave, though, the oscillations or vibrations are in the same direction as energy transfer. So this one over here, if you've got, if you decrease the volume, because we know that PV is constant at a constant temperature, therefore the pressure is inversely proportional to the volume. If you decrease the volume, we increase the pressure, and the reason for that, the explanation, is because if you make that volume smaller, the particles which are going side to side at the same velocity or the same speed, they're going to have more collisions per second with the walls because they're closer together. Again, this is kind of using your knowledge from GCSE and maybe just delving a little bit deeper. Can you explain why when you decrease the volume, we have a higher pressure? Then beta minus, this is our high-speed electron. What happens is that inside the nucleus, a neutron changes into a proton. So the neutron becomes positive, and to conserve charge, it ejects a negative electron, which we can give a symbol of 0e minus 1 to show that that's like kind of like an anti-proton, I suppose. It's not an anti-proton, but it's basically the opposite to a proton. So the Z number, the number of protons, goes up by 1, but the number of nucleons, the total number of protons and neutrons stays the same, and that element will change to a different element. On the 26th, we've got the 2 exponential graphs on the same axis, and this is important. What we've got is y equals e to the x and y equals e to the minus x. You might not know what this means, it doesn't matter, you can Google what this looks like, but on the same axis you'll realise that both of them go through the point 0, 1. So both of these cross the axis at the same point. This one is getting steeper, this one less so. Now, if you've got a constant volume of gas and you decrease the temperature, then the pressure is going to be going down. And the reason for that is that the particles or the molecules inside, as you decrease the temperature, they move slower. And that means in a certain amount of time, because they're taking longer to maybe go from one wall to the other and back again, there's going to be less collisions per second. And when and because they're moving slower, they're going to have less kinetic energy. So the collisions aren't going to be as big, and that means the pressure goes down because the force is smaller. For this one, we've made a massive assumption that the mass of the rocket stays constant. So the total energy is going to be equal to the increase in kinetic plus gravitational potential. Using the two equations and the data here, we can just work out these two things to find the total energy gained, or the energy transferred from the fuel of that rocket to its kinetic and potential energies, is just 2.07 times 10 to the 10 joules. On the 27th, we begin with a definition, just simple knowledge that you need to know. Here we've got specific heat capacity that you would have done at GCSE probably. So the specific heat capacity is just the energy required to raise a kilogram of a substance by 1 Kelvin. Now, we might have used degrees Celsius at GCSE, and that's still correct, but we tend to use the absolute thermodynamic scale, the Kelvin scale, a lot more, especially when we're looking at things like gases and so on. Now, explain the effect that increasing the temperature of a gas has on its volume. Well, if the pressure stays constant, as you heat something up, the volume increases. And this is because the pressure is related to the force. And what effectively we now have is the particles moving quicker. But if we have a bigger volume, it's going to take them longer to go from one side of that container to the other. So there'll be less collisions, but each collision provides a little bit more force, which overall means the pressure stays the same. If you're not sure about that, don't worry, your teachers will explain it to you properly as you go through the course. I now plotted some data. This one here appears to be anomalous. There's definitely a link between the extension and the energy, where there's this kind of y equals x squared relationship. I plotted it and I put in a line of best fit, a curved line of best fit. Now this was not my best line of best fit. It wasn't a particularly smooth curve. I'm sure the ones that you do are going to be so much better. Now, 30th of August, this is easy. Use your pencil and just start by moving the paper, committing to your line, and then you can draw it in. Okay, we've got some here which are different shapes, and actually these do mean something. So we might have maybe this exponential decay, and you have different sorts of exponential decay depending on how depending on the decay constant potentially. We also have this graph over here, which actually starts at a certain value, goes up to a maximum, and then it decreases. Now, you might think that's a bit of a weird curve, but actually that's what happens where we have something called resonance of objects, where they, at certain frequencies, start vibrating a lot. So that's the kind of resonance curve that you might see for objects undergoing a simple harmonic motion. Oh, have I missed out on a day? Okay, that's the 27th. Oh yeah, 27th, 30th, I should have noticed that. Let me put this back by a day. Apologies about that. I'm sure the editing will make it all clear. Okay, 28th of August. We're going to just use or calculate the values of sine theta. Now, my calculator, when I turn it on, it might be a bit hard to see, but up at the top there's a D up here, and that means the calculator is set to degrees. On this calculator, if I do sine 0 equals 0, so that's 0.000 to 3 decimal places, as it says here. Not significant figures, decimal places. And then I can just do sine 30, to use your calculator, and these are the values that I got. This one over here is a repeat of another question. Now, you might have found it difficult the other day. You might have looked at my work on the sheet. You might have watched my video. But what I want to do is tricky things. I want to ask you them several times, this spaced repetition, which will build up your knowledge. So here, F equals ma, A is equal to V minus U over T, substitute it in, look at this. We can then use the equation for momentum to find that the force is equal to the rate of change of momentum. Okay, you might not have done it okay the first time, a few days ago, but now it should hopefully be a little bit easier. For this one, I'm using the equation that says n1 sine theta 1 equals n2 sine theta 2. Now there's different equations, different exam boards write it out in a different way. We've basically got the refractive index of the first material, N1, the refractive index of the next material, and now we've got θ1 and θ2. Now this probably isn't taught for a lot of people at GCSE, because overall lots of people are really bad at taking sine of angles. But now you're better at that. I know you are, so you can do this. And this gives a value of θ2 as 30 degrees. Basically, as you have a higher refractive index, there's going to be a lower speed for that wave, and therefore sine I, or the angle of I, is going to be bigger than the angle R of refraction. So on the 29th, we're going to be looking at cos theta, and you might look at the link between cos theta and sine theta and see how these two numbers are related. Then we're going to have how an object can accelerate if the speed is constant. So this is for objects moving on a circular path, where because acceleration is a change in velocity and the direction is changing, that's how they can go at the same speed, but they're constantly accelerating. Okay, so that's going to come up quite a lot, maybe towards the end of year 12, beginning of year 13, when you start to look at circular motion. And here, I've got some resistors. I've got them connected in parallel. And the most important thing is to draw your circuit diagram. Again, I label stuff on the diagram. I use different colours, which you don't have to do, but I think it helped the explanation. I worked out the current separately because both of these have 1.5 volts across them. And then the total current is just these two numbers added together. And yeah, simple circuit problems, you're going to get very used to them, especially in year 12. That's the 29th. Now we're back onto the 30th, as I said before a few minutes ago in this video. And then the next bit on the 31st, is, have I lost another page? 30th of August, part 2. There we go. Draw an appropriate line of best fit for the following graphs. Using a ruler for these ones, that's an anomaly, so that was discarded. And these ones here, a line of best fit in physics can be a curve. Often in maths, the line of best fit is straight, but you can have a curved line of best fit in science. Trace the following curves yet again. You can do that. You did it yesterday. This one here goes up and goes down. And this one is actually related, or could be the shape of a curve. Let me just put my hand on this side. This could be a curve looking at the peak wavelength of emitted radiation, and how as you have something which is hotter, maybe the area under the curve gets bigger because more energy is being transferred, and also this peak here is going to shift to the left. So again, these curves, they will be familiar with you as you go through A-level physics. And then the final bit of August, we had again just some more lines for you to put in your line of best fit. Again, sometimes it's a straight line with a ruler, sometimes you just have to judge using I suppose experience, judging by eye, where your curved lines of best fit should go. So those are my answers, with a little bit of confusion towards the end for the whole of August for book 1 for the daily workout. Okay, tomorrow we start September. It's getting nearer to that start of term, and yeah, you're going to be fine. If you've done the work from July and August, you'll just be absolutely fine as you go into September and starting your A-level courses properly.